Hi everybody, welcome at tutorial 6 of our Extremes and Variability Day. For this tutorial, we'll be talking about non-stationarity, very important concept when you're working with climate records like we have done before. And the objective is really to understand this concept, for you to be able to explain it and to be able to show it in an historical record like we're going to do. But maybe first a little bit of a recap. You have seen these types of time series now before of climate variables. In this case, we have sea level height at Hoek van Holland in the Netherlands. I should say it's annual maximum sea level height. And what we have done so far is fitted distributions to these, for example, the GEV or the normal distribution, and then use that in a frequency analysis. Frequency analysis is what we call the things that we have done so far, where we compute return periods and return values. Now, a question for you, and perhaps pause the video for a second so you can think about it. Do you think this record that you see here on the left would be appropriate for a frequency analysis, or what could have been some of the issues with it? Okay, if you have an answer on that, keep that in mind. So hopefully you've noted this linear increase of sea level heights in Hoek van Holland over time, right? There fits a very nice red line through it, a linear fit. And that's a different type of pattern besides that random noise that we found in the data so far. So the random noise of just sometimes being at high and sometimes being at low and mostly around the mean. You see that there's something added to that. And of course, we know, especially from all the classes that you've done with climate match so far, that this is due to climate change. Climate change is affecting sea levels, slowly making them increase. And we can see that in the record up here. However, how does that affect our frequency analysis? That's a very important question to ask. So for this exercise, what we're going to do is we're going to split our data into 4 climate normals. Climate normals are 30-day periods that reflect like a climate in a given year, right? So here we have the climate normal from 1900 to 1930, etc., all the way to our current climate normal from 1991 to 2020. I've given them different colors so you can sort of see the different patterns in there. So let's plot the histograms of these. That looks something like this. You can already see quite a bit in here that reflects that linear increase that we saw over time, right? You see that slowly those histograms are shifting towards higher values, higher sea level surface height values on the right. You see a shift towards the right. You have seen this before when we talked about distribution in climate. If you just quickly look at the moments, you see the following thing. So you see that mean is increasing. You see some funny things happening with the standard deviation, and also the skewness is changing over time. So that tells you already something, that our parameters will probably also be changing, right? Here I fitted a GEV distribution to those same 30-year periods, and you can see the following sort of pattern. It's nicer than looking at the histogram. The histogram is a little bit bulky as a plot itself. So here you can better see the differences, the more nuances within each. You see the shift towards the right. However, you also see other things happening. So maybe pause the video. I'm going to show you the parameters for each period in the next slide. But pause the video and try to think what, how that would look like, what you think the parameters changed into. So here you see our 3 parameters: location, scale, and shape, and our 4 periods. And one thing that we can see again is that the location parameter is shifting towards higher values over time. The system is getting more, or sea surface levels are getting higher over time. We know that from climate change. But you also see that in the scale, there's something interesting happening. For example, in the first period, it's 74. And then in the next period, it gets 50. And then it turns up to 74 again. And then back to 50. There seems to be something cyclic in it. We know from many cyclic patterns in our climate systems, these climate modes like ENSO or NAO could very well have to do something with this. So you can see the effect of that in this breakup of our record. The shape parameter is, of course, also changing. However, I will be making a note on that the shape parameter is very much affected by individual extreme events. So splitting up our records in 30-year periods is a little bit too short to estimate a really good shape parameter. So I wouldn't put too much value on that particular thing. You would need bigger time periods, maybe 50 years or 60 years, to really identify properly the shape parameter. Okay. So when we have done our frequency analysis before, we assumed this thing called stationarity. We assumed that the distribution that we use was producing the complete record over time. So, like flipping that sentence, the record that we saw came from the same distribution. However, you have now seen that these parameter values change over time. It's very unlikely that this data came from the same distribution throughout the whole period. And this is what we call non-stationarity. And any of the parameters of our distribution, in our case in GEV with 3 parameters, but perhaps there are 4 parameter or even more parameter models that you have, we call this non-stationarity. And it's something that we have to take into account. Now, what explains non-stationarity? I think we all know the answer to that. It has been very thickly laid up on this course, of course. Climate change, right? Some go as far as saying that stationarity is just that. There's no stationarity anymore due to climate change. Climate change, for one thing, is at least affecting many of these systems. So it's very big assumption to say that nothing's going to change. So how does that look like for different types of parameters? How do they reflect in these different records? I have here 3 graphs next to each other. And each of the graphs, we can see one specific parameter of a GEV being changed. So I will give that you as an exercise now. If you pause the video, just assign each of our 3 parameters that we add, location, scale, and shape, to one of these graphs. And we'll look in the next slide if you were correct. Okay, hopefully you assign, hopefully you have the correct answers as they are given here. So with the shape parameter, you can see how the mean and the variation in general stay similar. However, sometimes extreme events are much more extreme, and they are getting much more extreme. This is a thing we see very often in our current climate. Location parameter looks very similar to what we had seen before, of course. There's an increase overall. And the scale, here you see that the scale is actually changing or reducing over time. The system is becoming almost more stable. It's not just the extremes, but it's all the values that are sort of spread more around the mean. So again, stationarity is probably that. So we need to figure out ways to account for this in our frequency analyses and in our studies of extreme events. We need to figure out a way in which we can include time. We're going to do that in tutorial 8. For the next tutorial, however, we're going to first look at climate projections into the future and see how those are different using similar techniques as this.